All right, so far we have looked at arithmetic sequences and arithmetic series. Okay, and the difference between the two of those is that an arithmetic sequence is just a list of numbers that have a constant difference between them, and then a arithmetic series is the sum of that list of numbers. Okay, now we're going to start looking at geometric sequences and series. So still sequences and series, so the same idea of a list of numbers or the sum of the list. Okay, but arithmetic versus geometric. Arithmetic is when the terms have a common difference between them. And geometric is when you're multiplying. So instead of adding between terms, you're multiplying between terms. Okay, so it's a sequence in which the ratio between any term and the previous term is constant. Okay, it's when you multiply by a constant, which is called the common ratio, R, to get from one term to the next. Honestly, I don't know why I put both of those sentences there. They pretty much say the same thing, except in the opposite order. We're going to come back to the formula in just a second after we think about this a little bit, okay? So looking at this example, we want to know what the 10th term of this sequence is. So it's pretty easy to figure out what R is if you look at this. You're just figuring out what am I multiplying by over and over and over. Well, to get from 2 to 6, I multiply by 3. From 6 to 18, I multiply by 3. 18 to 54, multiply by 3. Ergo, my common ratio here, R, is 3. We're multiplying by 3. Okay, so let's think about how we do this. I could just keep multiplying these numbers by 3 until I got to the 10th one. That would get me there, but obviously we want to try to figure out some shortcuts. It's going to be a pretty big number. So let's think about this for a second. Okay, so when we have our sequence here, if we want to go from A1, the first term, to A2, we're going to multiply by R one time, right, to go from the first to second term. If I wanted to go from the first term to the third term, I'd have to multiply once to get to the second term and then another time. So I'd have to multiply 2 times, right, to get to the third term. If I wanted to go from the first to the fourth term, I'd have to multiply to get to the second, and then the third, and then the fourth. So that's going to be 3 times that I'd have to multiply. Okay, and you're going to notice this is a very similar pattern to what we did before with arithmetic sequences, right? Except instead of adding, now we're multiplying. Similarly, if I wanted to go from, say, the 5th term to the 7th term, right? Well, I'd have to multiply once to get to the 6th term and then again to get to the 7th. So that would be 2 times. Okay, and you can see this pattern that's developing, right? The difference between these two numbers tells you how many times you're multiplying. So if I want to go from a sub 1 to any old a sub n in this list, I'm going to have to multiply n minus 1 times. Great. All right, so let's go back and look at this guy here then. We want to figure out the 10th term. Well, if I want to get to the 10th term of this sequence, starting from the first term, I'm going to have to multiply by my common ratio, which we figured out as 3, right? And how many times am I going to multiply this? I'm going to have to multiply this n minus 1 times, right? Well, I don't want to have to multiply, like actually write out R a whole bunch of times. But if we think about it, right, if I multiply by R twice, that's R squared, right? If I multiply by R 3 times, that's going to be R to the 3rd. So if I have 3 R's, it's R to the 3rd. And now I'm saying I want n minus 1 R's. So I'm multiplying by R to the n minus 1, or 10 minus 1 in this particular case. Okay, so I'm starting with my first term 2, and I'm multiplying by 3, 10 minus 1 times. That's going to get me to my 10th term. Cool. All right, so this is where my handy dandy calculator comes into play. I'm starting with, no, you can't multiply 2 and 3 and get 6 and then raise 6 to the 9th power. That doesn't work. You can't do that, right? That's not how order of operations goes. You have to do exponents first. So I'm going to do the 3 to the 9th first, and then I will double that, and it works out to this lovely large number. So the 10th term in this sequence is 39,366. Okay, great. Okay, so then let's go back and think about what's my formula then. Okay, we didn't write down a formula yet. Let's go back and talk about what that's going to be. Well, for my formula, it's going to be to get to any term in the sequence, I start with the first term and I'm going to multiply by r. How many times? Well, the difference between these two. So it's going to be r to the n minus 1. So there's my little formula. But again, I think just using a little bit of logic is easier than memorizing these formulas. All right, this guy right here, we want to find the a sub 15 in this sequence. Okay, so I want the 15th term, and I'm going to start by figuring out what my common ratio is. So to go from 3 to 9 and from 9 to 27, hopefully it's pretty obvious here that your common ratio is 3. All right, so to get to the 15th term from the first term, I need to multiply by my common ratio 15 minus 1 times. Okay, my first term is 3, and I'm multiplying that by 3 to the 14th power. Side note, you could clean this up a little bit if you wanted to, right? Because they have the same base. You could rewrite this as 3 to the 15th power and just put that into your calculator, right? But that's because these ones have the same base. We couldn't do that here because they have different bases. Right? But same base makes your life a little bit easier. All right, so we multiply all this out, and it's going to be a rather large number. So we're looking at 14,348,907, right? Hopefully you picked up on this already, but geometric sequences get larger much faster than arithmetic sequences do, which makes sense, right? Because we looked at what we had before. Arithmetic sequences, we said, were linear equations. All right, geometrics are not. Okay, and we'll come up with a formula for that and talk about that again in just a minute. All right, this guy right here, if we know a sub 1 and we know our common ratio, we want to find a sub 6. Well, to get to a sub 6 from a sub 1, I need to multiply by my common ratio 6 minus 1 times, right? So we want to find a 6, but I know a1 is 12. My common ratio is 2/3, and I'm essentially raising that to the 5th power. When you put this into your calculator, make sure you use parentheses around the 2/3, right? Raise that to the 5th power, and then, multiply by 12. Okay, and don't forget you can change this into a fraction form, which is always more preferable, right? So I'm going to go to my math button here, and the top option changes things to fractions. So it's 128/81. Okay, and you want to do that because you don't want to leave it in a decimal form, because then you have to round. This is the exact answer here. If I had taken this and rounded it to 1.58, that's not an exact answer, it's rounded. Okay, so you always want to go for exact answers when possible. All right, so now let's take a look at finding the formula. So this one we want a generic formula, okay, where we have this sequence 2, 8, 32. Hopefully, again, it's pretty obvious here that my common ratio is going to be 4, because I'm multiplying by 4 over and over. All right, and then I want to set up my generic rule. So my generic rule, to get to any a sub n, I start with a sub 1, and I multiply it by my common ratio n minus 1 times. Okay, I want this to stay a sub n. I don't want to use the 32 because 1, it's not the end of my list. That's what the dot, dot, dot means. And 2, I'm trying to find a formula or a rule for this. So I want it to be kind of generic. But I will plug in what a sub 1 is. That's 2. And I will plug in r, which is 4. And we leave it as raised to the n minus 1. And that right there is going to be your rule. No, you can't put these two together, right? You could, we could pull some tricks where we rewrite 4 as a power of 2 and then combine it together. But we don't want to do that in this case because this describes what's going on really well in this sequence, right? You can clearly see that we're starting at 2 and multiplying by 4 every time. If I rewrote this as one big sequence, it would be a different way of describing it, but it wouldn't necessarily describe it as well. So we're just going to kind of leave it like that. But as a side note, you could rewrite this, right? Because I could make that 4 2 to the 2nd power, right? To the n minus 1. And then we could make that 2 to the 2n minus 2, and then add our exponents. So it would be 2 to the 2n minus 1. That is the same as this. But you don't have to do that. Okay, so that right there is our rule. And you're going to notice this is an exponential function, which makes sense. That's why it's growing so quickly. Okay, and you will see that happen. So geometric ones are exponential. They grow pretty quick. All right, and then finally, this guy down here. Now, this one, make sure you pay attention to because there's kind of a weird thing that happens in this one. Okay, so we have a sub 6 and a sub 8. We want to find our common ratio r and a sub 1. And you might be looking at this and thinking, oh, I can figure this out in my head pretty darn easily. But we're still going to walk through it, and you'll see why in just a moment. So to get to a sub 8 from a sub 6, I would have to multiply by r 8 minus 6 times, so 2 times, right? Okay, well, a sub 8 I know is 5. A sub 6 I know is 20. I'm trying to figure out what r is, and that'll be r squared. Okay, to solve this equation, I'm going to divide both sides by 20. 5 divided by 20, that's going to simplify to a fourth, equals r squared. And then when I square root both sides, be careful because the square root of 1/4 is not a half, right? Positive or negative half. Well, that's interesting. Positive or negative. Let's think about that for a second. So I'm starting with 20 and I'm ending with 5. If I use a common ratio of 1/2, right? 20 times a half would get me to 10, and 10 times a half would get me to 5. So that works, okay? If I used a common ratio of negative a half, 20 times negative a half is negative 10, and negative 10 times negative a half still gets me to 5. So that would work. So either one of these is possible. We just don't know, is this series staying positive all the time, or is it going negative on every other term? And there's no way for us to determine that from this information, okay? So if we're going to figure out what a sub 1 is, we're actually going to have two potential answers here, okay? We could end up with a positive number or a negative number. It might be the case, depending on what term they're asking us for, right? If they'd ask for a sub 4, it wouldn't matter because it would be positive either way. But because they're asking for a sub 1, it's going to be positive or negative depending. Okay, so we're going to have to kind of break this down into two different problems. Okay, so the first one we're going to look at is I'm going to look at it, well, if I use r equals 1/2, then you can pick either one of these terms to use, either a sub 6 or a sub 8, whatever your preference is. I'm going to use a sub 6 because I like 20 better than 5, right? So to get to a sub 6 from a sub 1, I multiply by my common ratio, 6 minus 1 times. So I know this is 20. I don't know what a sub 1 is. I'm using a common ratio of a half, right? And raising it to the 5th power. So solving this really quick, 1/2 to the 5th power, and then I'm doing 20 divided by that answer is 640. So a sub 1 would be 640. All right, if I use r equal to negative a half, similar idea. To get from a sub 6, I start with a sub 1, I multiply by r to the 6 minus 1. A sub 6 is still 20. A sub 1 is what I'm trying to figure out. Now we're using negative 1 for our r value, and we're still raising that to the 5th. So negative a half raised to the 5th power, right? And then I'm doing 20 divided by that is going to be negative 640, which you probably could have predicted pretty easily, right? So for my actual answer for this one, you're going to have two answers, and you're going to have to be specific. So we're going to have to say if r equals 1/2, then a sub 1 is 640. But if r equals negative 1/2, then a sub 1 is negative 640. And there we go. Okay, so that's just a exception that happens sometimes when you're looking at these guys that you just need to make sure that you are careful of and keep an eye out for. Okay, so that's geometric sequences. And again, the difference between arithmetic and geometric, arithmetic you're adding, geometric you're multiplying. And the difference between a sequence and a series is just a list of numbers. A series is the sum of that list of numbers. Okay, so that's it for geometric sequences. We'll look at geometric series next time.